Hello, everyone. Welcome. My name is Jennifer Nyman. I'm a senior principal at Geosyntech Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERTIP and ESTCP. I will be facilitating today's event. The webinar today focuses on DoD-funded research efforts to develop protective and environmentally friendly coatings for DoD ships and aircrafts. First, Dr. Eric Ketze of the U.S. Naval Research Laboratory will discuss the use of organosilane polymers in top coats. Second, Dr. Michael Brinza of the Naval Air Warfare Center Aircraft Division will present on the development of aluminum-rich primers. Each presentation will be followed by a question and answer session. We will conclude the webinar with a question and answer session with both of our speakers. The next two slides provide some instructions on watching the webinar. If you haven't done so already, you can download Zoom at the link shown here and given to you in your webinar registration confirmation email. If you can't download Zoom, you may view the slides using a compatible internet browser. And those include Firefox, IE, or Edge, and by creating a free Zoom account. Finally, if you are unable to view the slides or if your screen freezes, you can try key and control with F5 to perform a hard refresh. In case of continued technical difficulties, you can always download a PDF of the slides from the webinar webpage and then call into the conference line that was provided to you in your webinar registration email. We will also be live streaming the webinar on the CERTIP and ESTCP YouTube channel at the link shown here. Today's broadcast is listen only. You may submit questions to the speakers by using the Q&A box on your screen. You don't have to wait until the question and answer period to submit your questions. And in fact, it'd be great if you submitted them in advance of that session. When you submit your questions, please add your organizational name at the end of your question. And please don't submit questions in the chat box of the Zoom platform. That's reserved for any comments related to technical difficulties. And with that, I would like to introduce Dr. John Lascala, the CERTIP and ESTCP Program Manager for Weapon Systems and Platforms. Prior to joining CERTIP and ESTCP, John served as the Chief of the Manufacturing Sciences and Technology Branch in the Weapons and Materials Research Directorate of the DevCom Army Research Laboratory. Throughout his career, John worked on bio-based thermosetting resins for adhesives and coatings, and environmentally friendly polymers for composites, adhesives, coatings, and additive manufacturing applications. John is the recipient of numerous awards for his work on polymers, including the Presidential Green Chemistry and Engineering Challenge Award for Renewable Thermosets and the 2010 ESTCP Project of the Year. John, please proceed.
Thank you, Jennifer. I'm happy to welcome everyone to today's CERTIP ESTCP webinar. Next slide. The next few slides will provide a quick overview of CERTIP and ESTCP. CERTIP and ESTCP are the Department of Defense's investments in environment and installation energy science and technology. The programs report to the Deputy Assistant Secretary of Defense for Energy Resilience and Optimization, headquartered at the Pentagon. CERTIP is the Strategic Environmental Research and Development Program. It was established by Congress as a partnership between the Department of Defense, the Department of Energy, and the Environmental Protection Agency. CERTIP addresses high-priority environmental science and technology opportunities that focus on the top priority DoD requirements. CERTIP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program, in which we demonstrate and validate innovative. These investments capitalize on past investments under CERTIP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. Next slide. Advances in science and technology provide the DoD with the tools needed to effectively manage and restore its assets to protect troops, their families, the public, and the environment. CERTIP and ESTCP investments improve installation energy resilience environmental cleanup, UXO remediation, resource conservation, and the sustainment and maintenance of defense assets. Next slide. CERDP and ESTCP fund, monitor, and actively guide relevant and applied research, development, testing, and evaluation products for the DoD's top environment and installation energy challenges. Our programs currently fund over 600 active projects. To maximize research impact, CERDP and ESTCP collaborate with top talent across sectors. In 2023, we funded projects with 77 academic institutions, 91 federal performers, and 52 industry partners. Our innovation and technology development inform DoD policy to ultimately improve environmental and energy management. Our webinar series highlights outstanding projects across all of our main focus areas. The next webinar is an MRMEM webinar on July 11th, and will feature 3 of our projects on sustainable energetics. Registration is open for webinars through the end of the year. You'll find additional information about upcoming webinars at this link shown on the screen. All past webinars are archived and can be accessed using this link. I'd also like to remind you that you can get a copy of today's presentation that can be downloaded from the webinar webpage. And we would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at the end of the webcast. Now, just to mention, as far as today's presentation, it's on aviation coatings. Coatings operations in general are of significant environmental concern because of the high surface to volume ratios and because of both DoD and industry's reliance on coatings to provide many useful properties, including visual appearance, corrosion resistance, weathering resistance, and other functional requirements, all within a material combination that's only a few mils thick. At this point, though, I'm going to turn it back over to Jennifer to introduce today's speakers. Thank you for joining us. I hope you enjoy the webinar.
Great. Thank you, John. Now my pleasure to introduce today's first speaker, Dr. Eric Yepsey, a senior research chemist and group leader at the U.S. Naval Research Laboratory in Washington, D.C. Eric is the principal investigator of basic and applied research programs that focus on synthesizing novel organosilicon molecules, developing environmentally friendly and smart polymeric networks within DoD relevant thermal, mechanical, and performance properties, and determining the mechanisms of network degradation due to sunlight and chemical stimuli. Several of his coating technologies have been commercialized for defense and non-government applications. Eric received a bachelor's degree in chemistry from Duquesne University and a doctoral degree in organic chemistry from Virginia Tech. Eric, please get us started today.
Okay, thank you. I appreciate the introduction. Okay, so my talk today is on organosilane polymers for high performance and environmentally friendly DoD top coats. I apologize for the delay. Oh, there we go. Okay, so for the presentation outline, I'm going to give a little bit of background about DoD top coats and their general properties. Then I'll move into really the genesis of this technology, which came from a project for development of advanced top coats for ships. I'll move into the development of these organosilane polymers, how we then modified the technology for use on ships, aircraft, and I'll conclude with benefits to the DoD. Okay. So what are DoD top coats? All of our top coats that we use within the DoD are thermosetting polymeric materials. That means we take molecules that have reactive functional groups. These molecules are then mixed together to form covalent bonds within a network. And these networks provide very unique properties. Once these three-dimensional networks are formed, they cannot be solvated, they cannot be heated and reflowed. So they are a permanent network. And the reason why we use these thermosetting materials is because they provide very unique properties. Obviously, the main one is camouflage, right? Whether it's the picture of the aircraft or the ship below, we have some sort of a camouflage gray, or could it be green or brown or another color? But these thermosetting networks also provide exceptional thermal and mechanical properties, in addition to protection of our underlying anti-corrosive epoxy primer. Now, in the bottom left-hand side, I have a stack up showing what would be a metal substrate with a pre-treatment, a primer, and then a top coat, which typically on a lot of our assets is 50 to 70 microns thick. However, not all of the assets use a pre-treatment. That's typically relegated to mainly aircraft usage. Okay, so for anyone who's not aware, on Navy surface ships, the top coats that are used on the exterior freeboard are qualified to MIL PRF 24635 performance requirements. Now, this is the gray colored coating that we see when we typically would look out into the ocean and see a ship. So it's the coating above the water line, whether it's on the freeboard, which would go up from the water up to the main deck, or the superstructure, which would be all of the structure above that main deck, as I'm showing in the photo. Historically, and so I would say more than 50 years, silicon alkyds have been the technology of choice. And the reason why silicon alkyds were used was because they were a single component system, which that single component is designated as 1K, which is an all-in-one can solution. So similar to wall paint that you would apply inside your house, but a higher performing technology than wall paint that we buy at Lowe's or Home Depot. But this technology was very easy for sailors to use, specifically for forming touch-up and repair, as I show in the bottom right photo. But it had some detriments. And some of the big problems with it were that even though it was cross-linked, the surface remained relatively soft. So any sort of running rust that you would have coming down from protrusions on the ship, such as I show in the photo here of the stern gate, is that running rust would become easily embedded within the surface of the coating. These silicon alkyds would also easily chalk and degrade after 6 to 12 months outside in the sunlight. And because of that, just their exterior durability in general would be reduced, and that gray color would begin to fade to a lighter gray color over time, and sometimes even to a pinkish color, depending on the pigments that were utilized. So in the mid-2000s, several companies began introducing two-component or 2K polysiloxane technologies. Now, what was different about these technologies are that as a two-component system, they required metering and mixing of components. So now you're taking two different containers of components and mixing them in a very specific volumetric ratio in order to generate a coating with your requisite properties. So while this technology is a very good technology, it is difficult for sailors to utilize. Primarily because, one, they have to mix materials together in a specific ratio. These materials are often higher in viscosity than silicon alkyds, and so using them during hot conditions can be problematic. One can imagine, right, your pier side on the bulkhead of a ship during the summer in, say, Norfolk, that bulkhead in the sunlight can get up to 110, 120 degrees Fahrenheit. So a coating that may have a few hours of a dry time at 75 degrees in the laboratory, now that time becomes significantly reduced when it's on a hot bulkhead in the sunlight. So these technologies, as I said, there's been several companies that have produced and have qualified products. One of the examples I'll speak to is a technology just based on dual cure technology of epoxy and amine reactions with also a hydrolysis of condensation reaction, as I shown below. So again, you have a very highly cross-linked system. It provides very good exterior durability, but the problem with one of the problems also with two-component polysiloxanes is they have very limited flexibility, which I'll talk a little bit about on a subsequent slide. So the question was, well, is there an alternative to silicon alkyds and two-component polysiloxanes? Because as the Navy moved away from silicon alkyds into two-component systems, we still needed a single component system that was easy for sailors to use. And so we asked the question, is there a sailor-friendly, non-hazardous technology out there that can be utilized by sailors that would provide equivalent or better performance than what had already been qualified. So in 2008, under an Office of Naval Research Future Naval Capabilities project, we sent out a request for information. And several industry and academia institutions returned with information. And I'm not going to discuss all of the technologies, but the three main ones that we saw kind of over and over again was one, moisture cure polyurethanes, single component moisture cure polyurethanes. But this was problematic because they contain isocyanates, and isocyanates, while this technology is a durable technology, isocyanates are prohibited by NAVSEA. So this could not be used as an exterior top coat on ships. There were some who proposed single component acrylic polysiloxanes. Again, one of the main problems with this technology is that it's slow to cross-link, offers limited hydrocarbon resistance, typically higher, can be higher in VOCs for some of these formulations. And that's as a high gloss clear. So you can imagine if you have to add fillers and so on to even reduce it down to a semi-gloss finish, that you're even going to have even a higher VOC content within that coating. And then finally, waterborne acrylics and polyurethanes were proposed, but those were kind of non-starters as well because of drying and freezing issues with it at the waterfront. And so we thought, well, can we develop our own solution to solve this issue? And so what we did is we developed some novel polymers, which are these alkoxysilane terminated N-substituted, and N is just nitrogen substituted polyurea polymers. And these are basically in a truncated form, simplicity form, what I'm showing below in the chemical structure. So these polymers are materials, they can be synthesized in a high solid, they can be synthesized as high solids in organic solvents while still retaining low viscosity. The mechanism of cure is that these alkoxysilane groups, which I have circled here, these react with atmospheric moisture. They hydrolyze to form silanol linkages, and then adjacent polymers will cross-link with these linkages to form this rigid siloxane backbone, as I'm showing after the reaction arrow. However, the majority of the polymer is based on these aliphatic backbones, which provides very good flexibility and other properties to the network. So we kind of get the best of both worlds with these materials. So then what we did is we began developing our own formulations then. So we started with taking these polymers and forming haze gray single component polysiloxane top coats. The haze gray color that's required by NAVSEA is this 26270. We're able to get fairly close to that, but we don't have the equipment in our laboratory to color match specifically. So, we develop as close to a haze gray formula as possible. But the coating, when cured, had a semi-gloss finish. Our formulations were less than 250 gram per liter VOCs with no HAPs, no isocyanates or other hazardous materials. And we had developed the formulation so that it will sufficiently cross-link over a wide range of conditions, that being here about 50 degrees to 120 degrees Fahrenheit and 20 to 80% relative humidity. So the next thing to do is to begin performing testing in the laboratory. And so the testing here was performed according to MIL PRF 24635 Type 5 performance requirements. Again, this is the exterior top coat for ships. And so right away, doing a simple test like a MEK, methylethyl ketone solvent resistance test, you can easily see something like the silicon alkyd is rubbed through after about 58 double rubs, whereas the single component polysiloxane after 100 rubs, there's not even any marring or marks on that coating. So much higher cross-link density and solvent resistance. At the same time, if you perform a quarter-inch cylindrical mandrel bend, you can see that the single component polysiloxane can easily bend, the polymers can stretch, and there's no sort of cracking whatsoever on that sample, similar to the silicon alkyd. However, when we take the qualified two-component polysiloxanes, which possess a much higher cross-link density, as you can see, is after even bending them slightly, is that they all crack. And so this was just to show that not only can we have very high hydrocarbon resistance, but still retain very good flexibility as well. And then one of the other tests, right, of many tests that we had performed early on, was to demonstrate the weather resistance of this single component polysiloxane. And so what we did was we took 3 of the qualified products from the qualified product list, 3 of the 2 component polysiloxanes from the qualified product list, in addition to 2 of the qualified silicon alkyds, and we exposed them all to 4,000 hours of xenon arc weathering. And you can see here the polysiloxane at 4,000 hours still had a color change of only about 0.5, whereas the best next performer was a 2-component polysiloxane, which did fairly well at a delta E of 2 at 4,000, but many of the other coatings, even at 2,000 hours, had already had delta E changes of of a couple digits, which for some of them, specifically even the silicon alkyds, you can really see that color change away from a gray color to a white or other sort of colors. So during that time period, we had filed patent applications for the technology. This then resulted in 6 U.S. patents, which I have listed here, and those can be looked up. They're all public information. And so from 2013 to 2017, we had contracted NCP Coatings to help us optimize and produce these single component haze gray coatings under a NAVC funded project. So this was all done initially under government funded, and then eventually they had decided to separately license the technology for other sorts of use, which I'm not going to get into. So when working with NCP coatings, right, there's a lot that you have to do when you go from laboratory sample and polymer development, which we're working at quart samples, and the goal was to get up to producing 50, 100, 400 gallons of material. And so there was different optimizations that we had to do. We had to make sure the consistency. There were consistencies with producing the polymer, the order of addition with the reagents and components in the coating. But eventually we had settled on a formula which we deemed N-9999, and that formula had a VOC of 206 gram per liter, a flash point of 100 F, which NAVC coatings are required to have a flash point above 100, and then a dry time of 8 to 10 hours at these laboratory conditions here. For those who may not be aware, any new molecules that are developed, in order to use those commercially, whether it's a DoD or non-DoD application, they have to be still registered by the EPA. So this was something that had to be done before we could begin using these materials. And so I had spent time working with NCP and a third party in order to register these new polymers on the EPA's Toxic Substance Control Act new chemical inventory. So now that we had our material, we could move towards commercial applications. We began producing material in 50+ gallon quantities. Again, the number that top coat was N9999. We produced material. We ran through all the testing at NRL once again to confirm that it passed all, and it did. And then we began performing small area demonstrations on ships. So from 2016 to 17, again, these are under government funded projects. We performed demonstrations on several ships at around 400 to 800 square feet, where essentially we would just give the material to sailors. We would watch what they would do with the material, see how they prepared the bulkheads, whether they sanded or they didn't, whether they'd applied a new primer or not, and just ask them questions to obtain feedback on the product. Everything went well. And then in April of 2017, we actually had a very unique situation where the USS Essex, which is an amphib, was a few weeks out from their fleet week, and they wanted to repaint. I'll get into this on the next slide, but they wanted to repaint the entire freeboard of the ship because the two-component polysiloxane on it had begun to discolor and turn to a greenish hue. And so they wanted the ship to look nice, but they didn't want to apply silicon alkyd because they knew within a few months they were already going to have to start painting the ship again. And so this gave us an opportunity to do a very large-scale demonstration, which ended up being about 105,000 square feet of freeboard area. And so as I show in the picture here, so the bottom left-hand side, that is the USS Essex. Again, so you were having a polysiloxane top coat that was beginning to shade to a greenish hue after about 3 years. And so the ship's force, what they did is they went out and on as many of the, on the surfaces that they could reach with JLGs and by other means, they tried to abrade the top coat with 80 to 100 grit sandpaper and water wipe, but the vast majority of the ship received no surface preparation whatsoever. And so they just rolled and brushed the 1K polysiloxane top coat over the ship. And you can see here in some of the photos below, you know, on the starboard side of the freeboard, you can see two sailors up in a JLG applying the top coat over the aged polysiloxane. There's a picture towards the center where close to the water line, you can see them applying the material. And then the final picture on the far right is what the port side freeboard looked like after it was painted. So it took them a week to paint this entire freeboard. Again, it was 105,000 square feet, and the ship's force did amazing, and it looked great. And you know, after several months, in addition to all the laboratory data and so on, is that this top coat ended up being qualified to 24635 Type 5 Class 2 Grade B specifications in August of 2017. It was listed on the Qualified Products database. So moving on to aerospace top coats, again, for anyone who may not be aware, is that the top coats that we use on Navy or DoD aircraft and support equipment are two-component polyurethanes. Now, polyurethanes are a great technology, but they do have their inherent environmental drawbacks. The main one being that isocyanates are hazardous materials, and that can result in severe health issues, specifically sensitization upon dermal or inhalation exposure. Many of these formulations contain hazardous air polluting solvents such as xylenes, which are carcinogenic. And several of these formulations also contain per-polyfluorinated alkyl substances, or PFAS substances, which are typically in the form of fluoropolymers. And they do that in order to provide increased exterior durability. But as we all know, a lot of these materials are kind of being wrapped up in the PFAS legislation as we speak. So these top coats, there's basically three types of top coats that are all qualified to MIL PRF 85285. One of them being Type 5 or Type 1 for aircraft, Type 2 is for support equipment, and Type 4 is for aircraft with extended weatherability. Again, similar to ships, though, is that Navy aircraft were without an environmentally friendly top coat that offered equivalent performance to the two-component polyurethane. So they had polyurethanes which perform really well, so it wasn't a performance issue, but there was a lot of environmental issues that needed to be addressed. So once again, under a different government-funded project, we went back to the laboratory. We took our polymers that we had developed for the ship top coat and we modified those polymers. And what we did was we increased the length of the backbone, reduced some of the branching and some of the alkoxysilane groups, and modified a few other things. But we did that in order to essentially develop formulations that would have very high flexibility, but also still very good solvent, hydrocarbon resistance, and very good weatherability. We then took those polymers and formulated low gloss, or what we call camouflage grade top coats using inorganic pigments. That was then licensed by NCP to produce isocyanate-free, HAP-free, and formulations that were about 290 gram per liter VOCs. And the container on the right is a formulation that was a finally optimized formulation later on. Okay. So What we ended up doing, and this now became a ESTCP project, which is WP 10506, which I mentioned at the end of the talk. We then took those materials that were produced by NCP Coatings, and they were sent to the Naval Air Warfare Center Aircraft Division, where Mike Brinza works, and they ran through all of the performance testing according to MIL PRF 85285 Type 4 performance requirements. This is just a very small subset of the test, basically just showing that the camouflage gray single component top coat can pass, several of the more difficult tests, similarly to a qualified two-component polyurethane top coat. Okay, so then eventually, once we demonstrated that the top coat meets all the laboratory requirements, we moved on to doing demonstrations on aircraft. And so our first demonstration was an application on an AH-1Z Viper at Camp Pendleton in California. This was in March of 2019. And to do this demonstration, NCP Coatings produced two different colors of the single component polysiloxane top coat. One was a 36375 medium gray. The other was a 35237 blue gray. So the photo in the bottom left-hand side, this shows one of the artisan applying that medium gray top coat over a chromated primer. And one of the initial things we did during that application is we had the industrial hygiene office there to take samples of the air so that we could prove that there were no isocyanates in the coating. And indeed, they did that, and the results came back, and they showed that there were no isocyanates detected. The second thing we wanted to show was that not only can we apply the coating, but because it's a single component material, is that we can actually recover material that is unused. And so the photo in the center shows this is a 2-gallon pressure pot. There was two 2-gallon pressure pots that were used, one on each side of the aircraft. And so here, this is ended up being about half to about 3/4 of a gallon material that was unused. So we actually took that material out of the hopper, poured it back into the cans, sealed the cans, and then the following day, that medium gray color was used for stenciling over top of the blue gray single component polysiloxane. So essentially we had, aside from flushing the lines, we essentially had near zero paint waste because of using this technology. And then the other third thing to point out was that because it's a single component system, is that the artisans mentioned that you don't see ununiformity across the aircraft. So you can imagine when doing smaller aircraft, if you have to mix two component systems, say in a 4-to-1 mix ratio by volume, maybe one applicator mixes that at perfectly 4-to-1, but the other applicator mixes it at 0.9 to 4.1, right? So that small amount of pigment change can be seen by these trained artisans, but you don't have that issue with a single component system because everything's produced in the same vat at the factory. So it's all a homogeneous color across the asset. So what we did is, this was one of 6 aircraft that we had painted during a year and a half span. So we would monitor that aircraft every 6 months and go out and take color, DFT, gloss measurements, photographs. We would observe, is there any delamination or cracking, damage due to hydrocarbons, and so on. And basically what we saw after that 25-month period is that the top coats had a color change of less than 2, which was our objective. Also, the appearance was visually similar to all the other aircraft that were painted with 2-component polyurethanes. And in fact, most of the maintainers at Camp Pendleton had no idea that the aircraft even possessed a different top coat on it, which is really what we wanted to hear. So that was great. And eventually this top coat was then qualified to 85285 Type 4 Class NH. And that Class NH is isocyanate-free performance requirements. So finally, one of the things I want to end with is, this is a current project for demonstration and validation of gloss polysiloxane top coats on aircraft in GSE. So again, taking the same polymer technology, we had to modify the polymers in order to develop a suitable gloss top coat. You can see here with these top coats, we can produce gloss that is identical to type 4 polyurethanes. The top coats can, demonstrate 40% elongation, very good adhesion. And then I have some other data here showing that, even after 3,000 hours, we can have a color change of less than 0.5 with a gloss retention that is still above 86 after a 3,000 hours period. So the goal is to, once again, have NOC AD test all the laboratory performance of these top coats, and assuming that it meets all those requirements, go on to do demonstrations on actual aircraft in the field. For conclusions, again, single component polysiloxane top coats are an environmentally friendly alternative for the exterior of DoD ships and aircraft. Isocyanate free, no fluoropolymers, no HAPs. We can also reduce the generation of hazardous paint waste because it is a single component system. It has excellent exterior durability, and thus far has been fully qualified to the 2 performance requirements that I've listed below. And finally, to end, benefits to the DoD, right? Obviously, isocyanate free is the big one. So we're able to reduce or eliminate health issues and sensitization that would result from polyurethanes. We can also eliminate any sort of cost due to monitoring of isocyanates. From an exterior durability standpoint, because the top coats, specifically with ships, have a very good color and gloss retention, is that you can increase the operational readiness and reduce any sort of maintenance painting that would occur. And it's operational friendly, again, as in no metering and mixing of components, reduced paint preparation times, and homogeneous color across assets. So with that, if you have questions, these slides can be, or these 2 of these projects can be, I believe, downloaded by clicking on the links here. And if you have any specific questions, please don't hesitate to send me an email. So thank you for attending.
Wonderful. Thank you so much, Eric. To our audience, please do type in your questions at this time. If you go to the Zoom platform, there's a Q&A box where you can submit those questions. And we do have a number of questions. Eric, we received a couple of questions about low humidity conditions. So will the organosilane polymers work in below 0 conditions given the lack of atmospheric moisture?
No, you have to have moisture to cross-link the coating. That's obviously an absolute must. Typically, you need above 10% humidity. And then you don't want to go above 80% humidity as your max relative humidity. But if you try to paint in the desert, it would not work. The only way to get around that you would have to add moisture to the system. But as a produced single component system, that's correct. It would not cure at 0% humidity.
Okay, good to know. And then if there is a low humidity environment, does that affect the cure time for the 1K polysiloxanes?
It does. Again, once you get down close to 10%, it's going to be slower. It will cure. It's just going to be slower. And which is, again, why we say we typically, in a specific situation would be, say, for the ship top coat. So it's been stated on the data sheet to apply the coating between 20 and 80% humidity. So you don't want to be painting in the fog, right? Because that's going to end up distorting your finish of the final coating. And you don't want to paint when there's 0 humidity because it won't cure. So in that above 10%, maybe 15% range, it's just going to be a little bit slower. But as you begin to get above 20%, it cures sufficiently.
Okay, great. You showed a photo of a person using, I think, a respirator during application. Are there any inhalation risks associated with applying these coatings?
So we did, I should have included the slide. So any material that is sprayed, I would recommend a respirator being used, right? That it doesn't matter, what the difference in toxicologies are. But we have performed under the ESTCP project, the WP 2015-06. We did perform acute inhalation toxicity testing on the polymer. And basically what we showed was that the organosilane polymers were about 1/16 as hazardous as monomeric isocyanates and about 1/3 less hazardous than the polymeric isocyanates. Now, I'll caveat that with the acute inhalation test is performed at a very specific amount. So it could be that if we perform it at a higher dosage, we still have no issues with we still would have had zero issues with rodents, whether it be, from the, seeing issues with fur or breathing or even death. But that test is performed at a very specific amount. And so that is the only data that we can really generate from that test. So still less hazardous than isocyanates is the main point.
Gotcha. Good to know. And then we have a couple of questions about applications of top coats on top of other coatings. So are there any adhesion problems if you apply one of these top coats on top of another top coat?
So in the case of when you're applying over an aged coating, we have not seen any sort of adhesion issues. And a great example of that was when I was talking about the surface ships. So the 2-component polysiloxane, which was aged by 3 years, the sailors had just roll applied the top coat right over top of it. And even before they did that large scale demonstration, we had went onto the ship and found probably again a 400 to 800 square foot bulkhead. And we did that test where we rolled the top coat over areas that had zero surface prep whatsoever. We let the coating cure out for a week or two, and we came back and we performed X-cut adhesion tests directly on the ship to show that it had good adhesion. If the top coat that you're applying over was a recently applied top coat, a light abrasion with sandpaper is all you need to have sufficient compatibility and adhesion over that. So.
Okay. And then also, what about applying them over non-chrome primers?
We have done that work. Yeah, I haven't showed that work and have not seen any issues over non-chromated primers.
Okay, great. This next question is from the Naval Air Warfare Center Weapons Division. The formulation for aerospace had a larger delta E than the current PU compliant coating. So did the fillers or colors cause the delta, or was it due to recomposition from the testing related to scale and cost?
No, so again, that was an earlier formula that I was showing. I believe, without going back to the slide, I believe it was a color change of 0.8 or so versus 0.7 compared to the polyurethane. But they, with a few tweaks, that has now come down, and the polysiloxane top coat, I believe now is right around like 0.5 delta E with the formulations that are currently being produced.
Okay, great. And then what about these compounds at the end of life or before repair? What is it like to strip and remove them?
So your typical paint strippers will work. From an aircraft standpoint, the ESTCP project had also involved the Air Force. So Diane Burmaster and others from AFRL, they had performed stripping with both hazardous, I believe, so methylene chloride and then benzoyl peroxide-based strippers, and showed that both of those would easily remove the coating, up to 100% or whatever the requirement is. So the same sorts of strippers can be used if that's what the question is.
Perfect. Great. And one final question for you before we move on, Eric. How Has there been any evaluation of UV transmission through the coatings?
Not specifically, no.
Okay, wonderful. Well, thank you, Eric, for the wonderful presentation. And to our audience, Eric will come back online at the end of the webinar to answer a few more questions. So now it's my pleasure to introduce our second speaker today, Dr. Michael Brinza, who is the Science and Technology Lead for the Materials Protection Technology Branch at the Naval Air Warfare Center Aircraft Division. He has served as a subject matter expert for paints and coatings since 2014, advising many Naviair program offices on the selection, use, and performance of coatings and materials for corrosion control. Mike has been the principal investigator of projects funded by ESTCP, the Naval Innovative Science and Engineering Program, Office of Naval Research, and various other DoD sponsors on research, development, and demonstration of alternative corrosion inhibitors and polymer chemistries for coatings. Mike earned a bachelor's degree in chemistry from the George Washington University and a doctoral degree in physical chemistry from the University of Maryland. Mike, please proceed.
Yeah, thank you, Jennifer. Can you hear me okay?
Yes, sounds great.
Okay, great. Well, thanks everybody. I appreciate the good introduction, and 1 second while I get the slides moving. And thank you to Eric for a very thorough explanation of a project to develop coatings from a basic technology idea all the way through implementation on DoD aircraft, which basically is the outline of my talk as well. As you saw on the introduction slide, there are multiple layers in a protective coating stack up for DoD assets, and switching to a different layer here, I'm going to describe where the Navy is with respect to protective corrosion inhibitive primers for naval aerospace and ground sport equipment assets. So I'll talk you through what we've done in terms of the formulation development and underlying technology ideas, how we've matured that to a manufactured product, where we are on testing those products in terms of our specifications, QPLs, and then the ESTCP project that we are partway through now, which is meant to demonstrate the coupon level performance on Navy assets and DoD assets. So I think we all understand fairly well why we have these projects, and that's because we have environmental or worker safety restrictions. In the case of aluminum-rich primers, the DoD has regulations that require us to minimize the use of hexavalent chromium, which has been for a century now the preferred corrosion inhibitor to protect most substrates. Specifically works well on aerospace aluminum and mixtures of metals like aluminum and high strength steel or titanium fasteners. But as you can see on the picture of the right, which was a structural part of a Navy aircraft, even with these heavy metal based coatings, we still see a significant amount of structural corrosion and galvanic corrosion on our aircraft. And so the twofold goal is to get rid of chrome, but also improve performance in our protective primers. And like I said, we've known this is an issue for decades. I think everybody here is well aware of studies back into their childhood or before then, which show that chrome is a carcinogen and bad for the environment. Where we got interested in developing the aluminum-rich primer is from the idea that it's not a unique idea either, that there are plenty of coatings that use a protective pigment which is anodic to the substrate. You've had zinc as a coating for steel substrates for many decades, and in the 2000s came to the forefront that magnesium as a aerospace corrosion inhibitor, or at least for an aerospace aluminum corrosion inhibitor, is a potentially viable anodic material. But we evaluated it and found that it wasn't particularly optimized for the Navy environment, which is very corrosive, as you can imagine. And so my predecessors began work about 15 years ago to develop a anodically active primer that was hopefully as good as, if not better than, hexavalent chromium. And part of the reason we were able to do this is because of work that was performed by NAVSEA 25 to 30 years ago, when they began producing ship substructure out of aluminum instead of steel for certain classes of surface ships. The traditional zinc anodes were not electrochemically suitable to protect the aluminum substructure and superstructure. And so NAVSEA actually developed aluminum anode chemistries and published them under different patents and mill specifications that were electrochemically matched to protect 5,000 series aluminum surface ships. And so because the electrochemistry of the structural aluminum on aircraft, the 7,000 series, is not all that dissimilar to the Navy ships, these anodes were well matched in terms of open circuit potential and anode efficiency to protect our Navy aircraft. Likewise, they're suited for aircraft use as opposed to zinc or some of the other alloys, because aluminum anodes are lightweight, and we have the ability to tune their activity, and I'll explain this in a minute. We can tune their activity by playing chemical tricks or depositing certain things on the surface of the pigment itself. And so in those 15 years of development, we did two things here at NOC AD. We ourselves took aluminum powder and blended it into many, many formulations of primer with the sole purpose of increasing corrosion resistance in relevant test cases. And so we turned what knobs we had in the formulation, or what knobs we were understanding, in order to determine if different constituents of the coating or different changes to the coating constituents would give us a better electrochemical response to the salt fog testing that we perform. And the things we had at our disposal to change are the binder. So like Eric described, you can substitute one polymer for another, and with some degrees of freedom, you're able to change the physical and, in this case, electrochemical properties of the resin itself. And then we could also change the pigment. And by change the pigment, I mean we spent a good amount of time developing other pigment compositions that, when you put in a coating, are electrochemically matched to the substrate. And so we had a general idea of what's the right amount of potential difference between the 7,000 or 2,000 series aluminum substrate that we'd use as a test panel and the coating itself, which can be measured in an electrochemical cell. In addition to that, there are lots of theories in terms of what makes a metal-filled coating effective electrochemistry. People have studied this for a number of decades, and what pops up is under things called percolation theory is the idea that surface area of the particle, as well as contact of the particles between each other, is really important to have higher or lower degrees of electrochemical action or spread throughout the coating, where it is contacting either a different alloy like a fastener or a defect like a scribe through the coating. So we changed the size and shape of the pigment methodically and blended those into standard, maybe even simplified laboratory formulations to understand the impact to corrosion resistance. And in support of some of the maturation work that I'm going to explain in a few slides, the Navy was funded to explore how can we make this a producible and therefore manufacturable pigment and manufacturable coating. Additionally, I'll explain that we have sometimes done chemistry to the particles themselves, and that's a wet chemistry step in which we passivate the surface. And the reason to do that is to stop the reactions that you don't want to occur while allowing the electrochemical transfer between the particle and the substrate. And so we've played around with the types of chemistries which make sense to deposit onto the particles, if at all. And then finally, because we had a need to reduce pigment loading, as obviously the more pigment available in the film, the better it has a chance of contacting and then performing in the electrochemical reactions. But that might have negative effects on some of the other properties of the coating, like flexibility, adhesion, as you had learned in Eric's talk. And so we had a need to reduce pigment loading, and we were able to do that by incorporating other classes of corrosion inhibitors in minor amounts within the film. And through studying what is the right way to move inhibitors to different surfaces, we learned that there's specific classes of inhibitors that are compatible with the aluminum-rich primer, and plenty that aren't, unfortunately. A lot of that work was validated later on by modeling that we put out on an SBR contract, and Cordessa as a company was able to show through electrochemical models by which they built out sort of geometrical representation of a film and then changed a lot of those characters. The electrochemistry of the anode alloy and pigment itself, the surface chemistry of it, you're able to measure that in a simple flat cell, the electrochemistry of the resin. And so they were able to confirm what we had learned through iterative experiment. And so that was really helpful to learn. And because of that, we learned that the biggest contributors to the performance of the film are the resistance, or effectively, or impedance of the resin matrix, as well as the size contact of the particles and the surface chemistry of them. And finally, we didn't just develop a coating itself, but we, as the Navy, developed a series of test methods by which we wanted to make sure we were evaluating the films in the correct way. And there's lots of different specs and standards out there for evaluating coatings in a galvanic manner. But we wanted to make sure two things. We wanted to make sure that the performance of the coating could easily be replicated in chambers as well as outdoors, and was also later validated on aircraft to have the right representation of coating performance when comparing one to another. But also, as I'll explain in a later slide, we need a coating galvanic coupon test to be performed in the chambers that is easy to do, that is cheap and effective, and can be added into a specification. And so a lot of our more specialized materials, as you see on the bottom left, those are mock-ups of actual aircraft parts that have been cut out of a plane. And so you can go to perfectly fabricated assemblies that are the exact matches of materials you would find on aircraft, or you can go to test using very simplified off-the-shelf parts and hardware. And I think we pretty much did everything in between before we convinced ourselves that a simplified test is still acceptable. So that brought us to what we thought was a technology that was mature enough to have manufacturers evaluate and have manufacturers optimize for their own requirements and then feedback to us. And so we went to the Office of Naval Research and advocated for them to fund a large program, a future naval capabilities program that was meant to have paint manufacturers develop internally, scale up, and commercially produce these primers. And under that project, we had a number of companies that had licensed what were Navy patents for the technology, but 3 companies were performers in this maturation type of project. And their main requirements were to produce a coating itself that had better corrosion than the existing products. I think it's pretty straightforward. We prioritized the requirements in their contracts to the types of corrosion that are most prevalent and most harmful to Navy aircraft. And then there were a number of subsequent, what we might call second tier requirements that would meet environmental goals or meet usability concerns and enable all users or applicator sites to incorporate the primer as an alternative product. So things like we've talked about under the earlier discussion, VOCs, flashpoints, strippable via different chemistries or not, and application quality, dry times, and other concerns. So that brings us to where we are today. And that is, we had proposed coming out of the ONR FNC program, a ESTCP demonstration project, which is started in FY21. And because there were contract deliverables from the Office of Naval Research program that these 3 companies were giving us production scale batches, so tens of gallons or more of aluminum rich primer, our intention was to use those deliverables to test them for qualification to the mil specs. And if they were sufficiently good at preventing corrosion and met most or all of the other application and physical property requirements, then we could use those products to initiate on-aircraft demonstrations. To be fair, we had started evaluating the early immature formulations as well, and they had some issues that were meant to be worked through as we continue to mature, but we were able to use those as a means to show that even in a imperfect coating, the aluminum rich pigment did show promise for being a corrosion inhibitor in the field. And so what we did was initiate an ESTCP funded project, which had a couple big picture goals. One was baseline our product performance and develop a spec test method to be put into MIL PRF 23377, which is the military aerospace primer specification that my laboratory is the preparing activity for. We also serve as the test laboratory for all those products. Validate all the performance product submissions against each other and against the legacy chrome and non-chrome aerospace primers, and determine which of them are acceptable performance to be placed on a qualified products list and go forward into on-aircraft evaluations for what will be Navy authorization once they're observed in the field for a few years. Very similar to the polysiloxane project in terms of its linear transition between laboratory development, production, specification testing, and authorization for use. And so this project is focused on testing 7 products from 3 different companies. And we've determined that the best way to do so is in using this simplified galvanic panel in two different corrosion chambers. One is your standard ASTM B117, but another is the GMW cyclic chamber, which simulates drying and wetting. And we found that that's a lot more reliable at predicting coating corrosion resistance out in the environment than the B117. But likewise, we validated the performance of these products against each other at the Kennedy Space Center atmospheric exposure test site. And so we are in the process of publishing this coupon, how to make and expose it into our next revision of the specification to come out in short order for industry comment. Originally, you see there's 8 holes on those panels. Originally, we had included both stainless steel and titanium fasteners. And in part of wanting to simplify things for the coating manufacturers and other test sites who may want to perform this, we found that in no case over the last 10 years has the couple between titanium and aluminum, and that's 2024 as a substrate, versus stainless steel and aluminum. We have never found that coating performance at protecting corrosion from the one type of metal couple versus the other type of metal couple has ever changed. And so we were able to show that you can use a cheaper, simpler mock-up of a panel. And so, like I said, we now have a requirement, and the requirement, which I was really hoping would be quantitative. This has been challenging in that from application to application, I would like to see that we can bin a specific area around each fastener. And we use free available image analysis software to collect the amount of area around any given fastener, any given scribed fastener, and determine how much of it is undamaged substrate and how much is corrosion. Likewise, we've also gone in and done volumetric analysis and found that an aerial extrapolation is good enough to discriminate products against each other. But what I was hoping is we could say, here's a line, and this is the amount of area that can be undamaged to still pass the specification test. But variations in coupon quality in terms of the metal itself, the pre-treatment corrosion resistance, as well as thickness of the primer and so on, have made setting that chalk line very difficult. And so what we've decided to do is just use for now at least, use a chrome containing control material and expose our aluminum rich primers in the same chamber at the same time. Very similar to how the Air Force system specification has done over the years. Just showing you without, agnostic to company and product name, that we've found that there are at least 2 or 3 products. One of those aluminum riches has been pulled from testing at the company's request, but we have 2 different companies who have submitted products that are outperforming our best 23377 Class C products. And this doesn't include all of the panels or all the products that we've tested. It's just to show you that even amongst the class of material that you have on the QPL today, there's a fairly broad amount of performance it can be explained just from product variation. And so I'm hoping that we can tighten that up as well as we go along. But we have, I think, met the goals of the FNC and the ESTCP program, and that's we have products that are better at preventing galvanic corrosion than even the best chrome, hexavalent chrome containing primer that we have in the Navy today. So that leads us to where we are to wrap up this project, which is to demonstrate and validate that coupon level performance. Now, like I said, we started doing this a long time ago with the immature formulations, and that was just taking advantage of opportunities that various platforms or sites would give us to paint areas of their aircraft and fly them around and monitor. go through them kind of in an overview. The Army had collaborated with us under the ONR project and gave us access to one of their intermediate maintenance sites in Groton, Connecticut. They took a few removable but large components off an H-60 Blackhawk and painted them with the aluminum-rich primer, which gave them the opportunity to compare performance of the primer against the other areas of the aircraft, which were painted with chrome, I believe, maybe non-chrome, not 100% sure. So we had sent a team out to inspect those for 5 years and look for things like coating delamination, corrosion around fasteners, damage from the door sills and use and so on. And the results we found were mainly positive, comparing the test primer against the legacy. Likewise, we had sent some very early aluminum-rich primer formulations from one of the manufacturers to the U.S. Coast Guard depot facility in Elizabeth City, and they painted the tail boom of 2 helicopters, put them in service for 4 to 5 years. And while we weren't able to inspect these personally, the engineers responsible for that program were happy with the performance to the point where we've initiated a much larger demonstration of the technology with the Coast Guard. Similarly, we have been able to show that for Navy ground sport equipment, which is made of a mixture of steel, mild steel, high strength steel, and aluminum, that the aluminum rich is performing equivalently to the MIL PIRA or MIL DTL 53022 primers that they use, which is an Army specification for vehicles. And we painted a number of pieces of equipment before deploying them on aircraft carriers for approximately 2 years each, and comparing their average amount of corrosion to the neighboring pieces of ground sport equipment. And we're able to show that the aluminum rich performs equivalently or better and will be added to the authorized products on the ground sport equipment maintenance manuals as soon as we publish the specification. Here's another example, that a fire truck, which was out on the carrier for a number of years. Which brings us to Navy aircraft demonstrations. And like folks may be aware, we're undergoing this evaluation because there are non-chrome primers that are available for Navy aircraft, but for the most part, we have avoided using them in certain areas. And those areas are the ones where we cannot accept the risk of inferior performance for a protective primer. The things like primary aircraft structure and interior locations that are both hard to rework and hard to inspect if the coating doesn't perform well. Because we're able to show that that's exactly why we developed this primer, and that's the type of corrosion that one might expect it to prevent, the galvanic corrosion around fastener lines. We've been able to convince a number of programs to let us test the primer on their corrosion prone areas for the most part. So we started doing that back in 2018 with some particularly troublesome head hurters for the V-22 program. And you see there, I know the pictures are a little difficult, but this is a lower fuselage primary structure area called a chord. And as you can see there where we've applied the primer, it's an area that's at the bottom of the belly of the aircraft, and it's expected to gather water, oils, and other contaminants. And it's been a challenge to protect against. So we brushed the primer on to areas that had their corrosion removed. And after approximately 5 years in service, we were able to show that the primer is performing very well at preventing corrosion there. Which led us to entire aircraft demonstrations. That's the real goal of the ESTCP project. And we're doing that with a number of helicopters starting last year. The U.S. Coast Guard has lent us 5 H-60 helicopters, which are painted inside and out, all those interior corrosion prone areas, all the areas where you expect damage and water pooling and so on for a helicopter that flies just above the waves. And so what we're going to do is paint the interior, the exterior of the aircraft, and then go visit the sites, 5 different corners of the United States, and evaluate performance over the next 24 months. Similarly to the slide I showed you a few minutes ago, the Army has done or is in the process of planning a similar experiment on one of their H-60s, but in this case, they're going to do what the Coast Guard's doing, and that's inside and out, complete rework of H-60 helicopters, and then we will compare performance of the primer to another helicopter that was refurbished at approximately the same time and sent to the same site. And so that's the data that we would use to eventually authorize this for use on all Navy and Army and U.S. Coast Guard aircraft. So in conclusion, I believe what we have is a non-chromate containing primer that's based on aluminum as an anode to the underlying substrate. And we're able to focus our efforts on testing and transitioning this new technology where the previous non-chrome efforts have failed. And that's where we're leery of accepting the risk of performance. And because of that, we are likely to have a solution for a lot of the areas of priming aircraft that have yet to come up to meeting those DFARs and other regulatory requirements. Obviously, the benefit is chrome reduction in applying, chrome reduction in wastewater and sanding. But the important benefit is that if this works the way that the coupon data is showing us, we should be able to reduce the amount of corrosion maintenance, the amount of downtime, and the amount of part scrappage, which in and of itself is a huge cost and time and an aircraft availability driver for the Department of Defense. And with that, I thank you for your attention. Obviously, you're welcome to visit our ESTCP project page, and please reach out to me for any of this information or more, and any questions you have.
Great. And please submit questions for Mike using the Q&A box on the Zoom screen. First, Mike, when do you expect the revised 23377 to be released?
It is going out for industry comment as soon as I can get it to, and hopefully released sometime this year.
Excellent. The next question is about cost. How do the costs of aluminum-rich primers compare to other chrome and non-chrome primers?
I think from what I've seen, the companies have submitted their expectations of the cost based on requirements under the ONR project, and they're not out of line with costs of other non-chrome primers. Certainly a little more expensive than some of the more mature, legacy chromes, but the cost of doing the painting and the primers themselves should pay for itself with the reduction in rework and corrosion damage is what we hope.
Oh, okay. Next, this is a question from the Pennsylvania DEP. If the paint has low reflectance, is it difficult for wildlife, especially flocks of birds, to recognize ships or planes? And does that affect bird populations in flight?
Ooh, that's probably a better question for the top coat project. We don't typically fly aircraft with just exposed primer. The aluminum rich itself is not particularly more reflective than or less reflective than other primers. But I'm not 100% sure how we measure the wildlife viewing of aircraft. I do know, and I will say we have very stringent aircraft visual and other signature requirements. And I've seen calculations on the cost of loss of wildlife and so on. I'm not sure the DoD is at the stage where we can give up mission capabilities for realizing those cost savings yet, but maybe that's a conversation I'm happy to have later.
Sure. That's helpful. Thank you. We have a few related questions. Will Class G in the revised 23377 include an outdoor exposure requirement? If so, how long? Or have you already established a correlation between your test and outdoor or in-service performance?
Yeah, thank you. We have already established that correlation. And so my intention is that there is no outdoor 1 or 2 year test. In fact, I think the test, the only test that we're adding is shorter than the current scribed flat panel corrosion test. And that's 500 or maybe 750 hours of galvanic panels in the B117 and the GMW cyclic salt fog chambers.
Okay. Great. And then can you discuss any considerations for the disposal of the application equipment? Is there anything specific that you're aware of there?
In terms of the product, it can be disposed of as regular hazmat. Obviously, it contains solvents and so on. And the shop equipment, like the paint guns and pots and so on, are cleaned with standard epoxy solvents. So I don't believe there's any challenge to the disposal or the cleaning, if that's the intention of that question.
Mm-hmm. Yep, I think it was. Thank you. Okay, thank you so much, Mike. And at this time, we'll bring Eric back on the line and have a few last questions for each of you. So for Eric, do you have any insight to the polysilane performance with different color suspensions? And this is a question from the Coast Guard.
So we have a little bit of data from that, and right, your colors based on the different pigment chemistries that you utilize. All I can really speak to from the aircraft standpoint would be the 2 coatings that we had used during the ESTCP project, and the data shows that the coating that was more of a grayish color versus a blue gray had slightly better weather resistance, so photooxidative resistance, primarily because it did not contain a blue pigment. And one of the ways that, or one of the pigments that's often used in coatings is like a phthalocyanine blue, which can degrade. It can degrade it, or could even somewhat wash out from the surface. So it's true. It's kind of well known, I think, in the coating industry. Some colors are more difficult to stabilize than others, but we've mostly just focused on those 2 colors right now.
Okay, sounds good. Thank you, Eric. And then for Mike, what does the path to transition or implementation look like for these primers?
That's a good question. We have to collect the field data to show we validated our coupon findings on aircraft in the environment. I know that takes a long time and it holds up a lot of our implementation, but obviously that's important because it's hard to go back once we let the cat out of the bag. If we start painting whole aircraft and we have failures, that can be millions and millions of dollars in rework if we have to pull planes back in the depot. Beyond that, there is a significant amount of engineering work that goes into a change such as this. There are shop trials, there are drawing and process documentation changes, approval by all the platforms that intend to go forward with it, typically OEM involvement in changing their processes and specifications and so on. And so the path is to make sure that all those stakeholders are aware of the performance benefits and the ROI, and they're justifying the time it takes to do all that engineering work. So a lot of times we might have a product that works well on coupons, but it's hard to understand the massive amount of back-end engineering it takes to actually implement that.
That makes sense. Yes. Thank you, Mike. And then one last question for each of you. These questions are related. First for Eric, are there other DoD applications for the polysiloxane technology?
Sure, I think the technology could have applications on ground vehicles. So for the Army and Marine Corps, probably at the facilities, and I'm sure there are other applications that we could find. So yes.
Okay, great. And similarly for Mike, has the Navy attempted to use the aluminum-rich pigment for other applications yet?
We have to some success. The Navy uses pigmented coatings in a lot of different ways. We have requirements for conductivity, and we've been able to show for us several applications that you can mix the pigment into a paste or grease and match pigment which may have been a corrosion risk because of its identity. Now, some of those have eluded us in terms of the formulation is tricky, but I think that's one that's been successful, and one of the licensees has commercial products. We're also attempting to blend it into things like sealants and pastes to be used as installation media for things like bushing screws and fasteners and hardware, where you could benefit by having increasing amount of inhibitor in the galvanic couple itself.
Excellent. All right. Well, thank you to both of our speakers today and for answering all of the questions. We really appreciate it. Our next webinar in this series is on Thursday, May 30th. That will be on DoD-funded research efforts to develop tools to advance support for prescribed fires. And please visit the Startup in ESTCP webpage to register for this webinar and other webinars all the way through the end of the year. Before we conclude, I would like to remind you both the audio and a copy of the slides from today's session will be on the webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webinar. Thank you.